R5 in our network is going to be the source sending the traffic. R4 is going to be acting as the bootstrap router. R2 is going to be the R5, so is going to be R2, sorry. R2 is going to let BSR know that it's going to be the RP candidate, and R4 will have to let everyone else know. R6 is going to be just a regular multicast router, and R9 is going to be our client. And on the client here, we are going to be joining the group. So we want to get the traffic sent to 239.999. So the goal is to get the traffic from the source to this group here. So let me just write this out in red here. So R9 will be joining this group here. So this is the goal. Now, what are the prerequisites for multicast configuration? So I'm going to write here multicast configuration. So multicast configuration now. The number one prerequisite is fully converged unicast routing. Now, don't even try to build your multicast network before your unicast routing is fully converged. So in our example here, we need to have a fully converged unicast network. If there is no full reachability in this network, our multicast is almost guaranteed going to fail. So that's number one prerequisite. Number two prerequisite is enable multicast routing on relevant routers. And this is a step that can be easily forgotten. Number three is enable PIM on relevant interfaces. Now I'm going to give you an advice here, and this is going to be in green. If unrestricted, enable PIM on all the interfaces in the network. Number four, RP configuration. And here we are talking about static, BSR, or auto RP. Now, if you are given a choice, if the lab doesn't necessarily require you to run anything in particular, my recommendation is run BSR. So not static, run BSR, because you can use BSR messages for troubleshooting very, very effectively. Finally, join groups where needed. And test. And here I'm going to write in red that we are talking about IP IGMP join group. So this is the command that you will need to do. So these are the steps and the prerequisites for multicast configuration. Now, again, I cannot stress this enough. Fully converged unicast routing. Now, this is going to be number one issue that you are going to be dealing with multicast, is that you think that you have a multicast problem when in fact there is some unicast reachability problem. Why? Because unicast routing table is actually used by default for RPF verification. If your unicast doesn't work, your multicast will not work. Then make sure that multicast routing is enabled on all relevant routers. Enable PIM on relevant interfaces. As I said, if unrestricted, enable on all of the interfaces. RP configuration, static BSR or auto RP, my preference given to BSR, and then join groups where needed and test. IP IGMP group, and how do you test? You can test using ping and then the group address. Because ping is perfectly fine traffic generator. So given this knowledge here, if we go back to our example here that we need to build, what would be the relevant routers on which I need to enable multicast routing? So I will need to enable it here, here, and here. Now, mind you, R5, being the source, doesn't need multicast routing, and R9, given that we are unrestricted and that we are going to join the group from this interface here, also doesn't need to have multicast routing. So these are the relevant routers on which I need to enable multicast routing. What about PIM? PIM needs to be enabled on this interface here, this interface here, this interface here, this interface here, this one here, this one here. But it doesn't actually have to be enabled here or here. Why? Because this is a source. The source doesn't need any special configuration, just needs to be able to generate the traffic. And this one here is going to be acting as a client. And on the client, you don't need PIM on the client interface. So these are going to be the PIM interfaces. So this is the relevant configuration. So I know that I mentioned that if you're unrestricted, enable on all the interfaces PIM, but I'm not going to be doing that now because I want to give you an example of what is actually required in a network. So I'm going to now go not with what I would recommend is the best way, but what would be the absolute minimum configuration to actually get this working. Because I want to emphasize one thing, and that is that multicast is inherently easy to make work. If you satisfy these requirements here, if these requirements are actually in place, it would be very difficult to break multicast. Multicast wants to work, right? You actually have to make an effort to make multicast fail. And this is the mindset that I would like you to have when you go to the lab, that multicast is actually an easy thing to configure. And it is not actually that complicated. So let's start with our configuration. So I'm going to start by enabling multicast routing where it needs to be enabled. So I'm just going to say IP multicast routing here, and then on, oh, actually I forgot one thing. So all these things here, the BSR, the RP, this is going to be happening on the loopback interfaces. So these are going to be our BSR address. This is going to be our RP address. So obviously on these interfaces here, I will need to enable PIM as well. But here on this loopback on R6, I don't actually need to have it enabled. So this interface here doesn't need to have PIM enabled because it will have no special role in our configuration. So going to our configuration here on R4, where do I need to have it enabled? So let me just do it like this. So I'm going to look at R4 configuration now. I'm going to go to interface, actually interface loopback 0. I'm going to say IP PIM sparse mode. Then I'm going to say interface serial 000 405. I'm going to say IP PIM sparse mode, and I will have the same towards R2. So this is the configuration that will be very good to paste on R4. So this is what I'm going to do here. Let's go back to whiteboard and the notepad. So on R2, this is actually the interface that I'll be needing, 204, and I will need towards 6. So this goes in, so I can go back in here and paste this to R2. And on R6, I don't need it on the loop back, and I need it towards 602 and serial 020. So this is where I need to have this available. So now I have configured PIM just blindly. I haven't verified anything. Now, one of the most important verification commands when you are configuring or troubleshooting your multicast is show IP PIM interfaces. Now, this is a very, very useful command because it will show you on the router on which interfaces you have PIM enabled. So these are the interfaces where PIM is enabled. It will tell you in which mode you are operating. So here we can see that we are operating in PIM version 2 and that the mode is sparse mode. It will also tell me what is the neighbor count, how many neighbors I have on these interfaces. Now I can see that on these two interfaces, on the loopback and on a serial interface facing 5, I have 0 PIM neighbors. Now looking at the diagram, that's exactly what I have. On this interface here, I'm not expecting any neighbors because PIM is not actually enabled on this interface. So that's good. Now on this interface here, on the other hand, I do have the neighbor, and I can see that they have neighbor 1. Now, if I can do also show IP PIM neighbors to confirm, but I already know that I actually have one neighbor on this interface, and here is that one neighbor there. So I can see that this neighbor is in place, and this is good. This is exactly what I was expecting to see. Now, going back to my whiteboard, so this was verification on R4. Let's take a look at the verification on R2. Let's see what is happening on R2 now. So going back there on R2, I'm going to say again, show IP PIM interfaces. And here I am seeing 3 interfaces enabled for PIM, which is exactly what I expected, because I do have one interface here, and the loopback interface. And I can see that on 2 of these interfaces, I have neighbors. So on serial interfaces, I do have neighbors, so I don't even have to run show IP PIM neighbors. But I can, and this will exactly show me who the neighbors are. On R6, show IP PIM interfaces. Again, I'm seeing 2 interfaces here, and one of these has neighbors, and it is this interface facing R2. Now, this interface facing R9 does not have the neighbor. It has 0 neighbors here, which is okay because I have not enabled PIM on that interface here. So this is how I would build very quickly my multicast infrastructure, and this is really what my multicast infrastructure is. So this is the source, it's outside my infrastructure, and this is the client, and the client is also outside the infrastructure. So only routers 4, 2, and 6 are actually what form my MPLS, sorry, not my MPLS, but my multicast infrastructure. All those other routers are actually outside of my multicast domain because they are clients and sources. They connect to the domain, but they are not actually part of what I'm building. So what is going to be the next step here? The next step is going to be to test, do I have fully converged unicast network routing? I should have actually pointed that out, that this is already in place. So all my routers, so if I do show IP route, I'm running OSPF here. So all my routers actually have full reachability. So that is prerequisite that I have already met. I have enabled multicast routing on all relevant routers, check. And I have enabled PIM on all relevant interfaces, check. Now, RP configuration, static BSR or auto RP. In my case, I want to configure BSR. So let's go to R4 here, and I'm going to say in the configuration IPIM BSR candidate, and I want it to be loopback 0. So now this makes R4 the candidate for the BSR. If I do show IPPIM BSR, and this is the verification command that I can run, I will see that R4 is now the bootstrap router. It's not only the candidate, it is actually the bootstrap router. And I should be able to see that information on all of my routers that are part of my multicast domain. So R4, R2, and R6 will have this information. Of course, R9 and R5 will not have this information because they have absolutely no use of it. I have not actually enabled multicast routing on them. Now, the next thing that I'm going to do is I'm going to make my R2 IPPIM RP candidate, or loopback 0. So if I do show IPPIM RP here, now for a very brief period of time, I'm going to see just information that this router is the candidate. But in the meantime, I have actually received the BSR message that now says that, okay, you are the BSR. So now on R2, R4, and R6, actually RP map, sorry, I will have the information that for all groups in the network, R2 is the candidate. Now, let me explain the output of this command just a little bit. You see these question marks here. Now, these question marks here do not indicate any problem, but they may be cause of pain for you in the lab. Now, if in your lab you actually have IP domain lookup enabled, when you do show IPPIM RP map, your output is going to hang here because now router is trying to resolve the name. So this question mark here means that we couldn't resolve a DNS name for this IP address. So every time you run multicast commands, you might be in danger of these annoying delays. So my recommendation is no IP domain lookup, because then this failure happens immediately and you just get the output that you care about, because really in most cases you don't care about what is the name of these addresses. So now I can see that my R4, R2 and R6 actually have the information about who the RP in our network is. Now, let me show you one more thing. So I'm going to go on R4 now, and I'm going to say show IP mroute. Now, this is my multicast state table or my multicast routing table, call it whatever. Now, we know for a fact that I will be joining this one group here. So this one group here is irrelevant, so I'm not going to be paying any more attention to it. But this is for use with auto-RP. So I'm going to go to R5 now, and I'm going to say ping 239.999. Now, remember what are the roles in our network. R4 is the BSR, and R2 is the RP. But R4, for this traffic that will be arriving from R5, is also the first hop router, which means that this router will be in charge of actually registering this traffic with R2. So when I send this ping to 239.999, what I will be seeing is multicast state here. So I will be seeing 192.168.45.5, 239.999, but I will also be, so this is our S, G state, but I will also be seeing this state created here. Now I will be seeing this state created here as the result of this register message, but there will be no state on R6 because R9 has not joined this group yet. So I'm going to go to R5 and I'm just going to send one ping. So now if I do show IP mroute here, I'm seeing the state, and if I do show IP mroute here, I'm seeing that the state was created on R2. Now, you might remember that I said that you will also have star, G state, but that this state is actually irrelevant. Now, what is relevant state on R4 is actually this state here. This state here says that this is the source, and as I said, it will be 192.168.45.5. That's what we have, and 239.999. Now we can see that we do have an incoming interface, but the outgoing interface is null because we don't have any downstream routers that want to receive this traffic. Now it's a shame that I don't actually have a router between R4 and R2, that they are directly connected, so that I could actually show you that we are not going to have the state on this router between them, but I really didn't want this router here to be the RP. So maybe this would have been slightly better example if we had one more router in between to show you that there is no state on this router here in between, but this is something that I will leave to you as an exercise. Now on R2, I have this state created here. I know what is my incoming interface, where I would need to go here, because this is the same interface that will be the best interface to reach this address here, and I have outgoing interface null, which means that none of the clients are interested. So if I do show IP mroute on R6, I don't have any of this. So basically, our RP has learned where the traffic is coming from, it has created the state, and R4 here has the state. But the actual multicast traffic is not actually being transmitted on this link. This was a unicast encapsulated register message. Now, if I let enough time elapse, this multicast state will actually expire. So maybe we can wait for that to happen. We can see that it is actually 2 minutes and 6 seconds old. So it is going to expire after that because there is no source transmitting. So we have, some time before it expires. So I believe that this is the timer counting down 48 seconds before it actually disappears from our table. So let's just wait for that to happen. And the same thing we have here on R2. We have a countdown, and this one will actually expire in 25 seconds. 20 seconds. So 16 more seconds before we actually lose this state. And we can see it's very close. So this is a 3-minute timer here. And in 7 seconds, we are actually going to lose this state. actually we lost it here when this timer hit. When this timer hit 3 minutes, we can see that now we don't have the state. So after 3 minutes have expired, both routers here have lost the state. This state here now is going to disappear. Actually, this one might stay a little bit longer, but we don't have that S, G. I did mention that this one here is really irrelevant one. So at this moment here, we have lost the information about the source. The source sent just one packet, the state got created, and it existed for 3 minutes. But if the source is not transmitting, the states will be deleted. So let's now go to R9. So now there is no source. Let's go to R9, and on interface serial 020, let's join that group. So IP IGMP join group 239.999. So now what's going to happen is on R9, if I do show IPM route, I will not be seeing anything because remember, on R9, multicast routing is not actually enabled. But on R6, if I do show IPM route, what I am going to be seeing now is only *G entry. Why? Because R6 doesn't know who the source is. And what we can see here is that we do have an incoming interface. Why do we have an incoming interface? Because this is the best path to reach the rendezvous point. Remember, this is a shared tree we are talking about. And the outgoing interface, so we do have outgoing interface list. On the outgoing interface list, we actually do have a serial interface. Why? Because we actually do have an interested client here. Now let's take a look what's the situation on R2. Remember, R2 in the meantime has forgotten who the source is. So show IPM route here now shows me only *G entry that says incoming interface null. That means we do not know where the source is, but we do have an outgoing interface list. And here on outgoing interface list, we can see that serial 010 means that we do have a client. Now R4 here in the meantime, well, it still has this entry here. I have no idea. It will expire actually in 54 seconds. I'm pretty sure about it. So it has still not forgotten, but as I said, this is an irrelevant state. So let's send that one ping now from R5. So that ping now goes. So what has happened now is that R5 has sent the ping to R4. R4 has received this ping and has encapsulated it as unicast, registering it with R2. But R2 now sent it as multicast towards R6, who delivered it to R9. But if I go to R6 right now, I will actually see that in the meantime, this state got created. This state here, that is S,G state. So now at this moment, my router will start building that source base tree. This is going to happen totally outside of my control. Now, not totally outside my control, I shouldn't say that. I should say that it's going to happen by default. I don't have to do anything for that other tree to be built. Now, in this case, we have only one path back. So the shared tree and the source tree will be actually taking the same path, but that's okay. Now, I want to expand this example. I actually want to add something more to my network. So this something more is actually going to be one more interface between R9 and R6. So to do that, I'm going to bring in another diagram here. So I will put it in the background. So I'm just going to try to align it here with this. So I'm going to say here, okay, maybe I need to do one more thing. So let me do order, send it to back, and now this one here, analog. I want to actually delete this one. Okay, perfect. So this is the network that I'm going to set up now. So now, instead of having just a single interface here between R6 and R9, I'm actually adding a fast Ethernet interface, which means that that join group that I had on a serial interface, now it's going to be joining just the traffic here. So I'm going to move that join and join it on the loopback interface. So now the loopback interface on R9 is actually going to be the one that joins this group here. So let me go and implement that change. So on R9, I'm going to say interface fastnet 01. Is it 101? Yes. I'm going to say no shutdown here, and on R6, no shutdown, and show run interface serial 020. I'm going to remove this join group, and I'm going to go to interface loopback 0, and I'm going to join the group here. Now, in the meantime, I see that my OSPF actually converged on this fast Ethernet interface, so I do have full reachability there as well, and I can probably ping 05 and 45.5. Now, let's see what happens when I try the same ping. Now, when I try the same ping is actually going to be failing. So I'm going to keep sending this ping, so not repeat 1, I'm just going to say repeat 1,000 times and timeout in 1 second. So no matter how many pings I send now, basically they're not arriving on R9. Now, why? They are actually arriving on R9, but the problem is that they are arriving on R9 on one of these interfaces. It doesn't matter on which one. But then my join group is actually on a downstream interface. So now, in this case, on R9, I actually must enable multicast routing. Because at this point here, these IGMP joins that existed on serial 020, they were actually being heard by R6. So R6 was acting as the upstream router for the client, but now these joins are actually being heard by R9. So R9 now, instead of sending IGMP join to R6, actually needs to send a PIM join. So to do that, I actually need to enable multicast routing on R9. So let me do that. So I'm going to go to R9, and I'm going to say IP multicast routing, and then I need to enable PIM on all the relevant interfaces. So IP PIM sparse mode on the loopback interface fastnet 01, IP PIM sparse mode, and interface serial 020, IP PIM sparse mode. Now let me do the same thing on R6 interface fastnet 01, IP PIM sparse mode. So now PIM is actually enabled on all of these interfaces here. So I have PIM enabled on this interface here, on this interface here, and on the loopback. And multicast routing is actually enabled on R9, which means that in the meantime, if I do show IP actually on R9, if I do show IP PIM BSR, I have the bootstrap information, IP PIM RP map. I do have the RP mapping, which means that my ping actually works. Now, the reason why it works is that I have enabled PIM on all of these interfaces here. But what if I was restricted? What if my lab told me, enable PIM, or let's say that you were not allowed to enable PIM on fast Ethernet 01, so that we can enable it on serial 020 and on the loopback, but on the fast Ethernet 01, we are not allowed to enable PIM. Let's do that. So, or here. So on this interface here, PIM is not allowed to run. Let's go to our R9 and let's make that change. So interface fastnet 01, no IP PIM sparse mode, and on R6, interface fastnet 01, no IP PIM sparse mode. So now PIM is gone from that interface, and we can see that at this moment here, my ping is actually failing. Now, why is ping failing? Because if I go to R9 at this point, what is the traffic that I'm supposed to be receiving? It is traffic going from 192, 168, 45, 5 to the group 239, 999. So at this moment, I have to see which way am I supposed to receive this traffic. Now remember that simple idea that I have given you, that your multicast traffic by default will follow the same path as the unicast traffic from the client to the source will follow. So my multicast traffic actually needs to follow this same path in the opposite direction. So my traffic needs to go over this interface first, then over this interface, then over this interface, and then over this interface here. So if I take a look at my diagram, my multicast traffic needs to flow here, 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 and then over fast Ethernet. Why? Because if I take a look at this, this says 96, and 96 is exactly this fast Ethernet interface. So one of the best troubleshooting tools that you can use for multicast is to actually do the trace route, but it's upside down. You don't trace route from client to source. So not from upside down. So let me write that down. So it's not from source to client that you have to do. What you have to do is do the trace route from the client to the source, and then see if you have discrepancy with your PIM-enabled interfaces. So in this case, the reason why I'm not getting this traffic is because I have RPF failure here. Now, how can I confirm that I actually have RPF failure? Well, I can go to my R9 and I can do show IP RPF and do 45.5. Now, take a look at this. It says no route exists. But that's not true, because I actually do have the route. The route says it's, sorry, not for this, for 45.0. It says here that I do have the OSPF route, but take a look. It points out to the fast Ethernet interface. Now, how do I correct this problem? How do I make the traffic go where I need to go when I'm not allowed to enable PIM? Well, as it turns out, there are multiple solutions. So how to correct RPF? Now, you can correct RPF failure by modifying unicast routing. You can correct the RPF by using multicast, or let me write this down. There are multiple names for this next feature. You can use static RPF verification, which is sometimes incorrectly called static multicast routes. And you can use multicast BGP. Now, this one here is simple to understand. Now, simple to understand because the only thing that I actually need to do is make sure that R9 here prefers the path over serial interface instead of fast Ethernet interface to reach the source of the traffic. But for these two here, I want you to remember that it is all about the sources, not about the destination. This is about the sources. So what I need to do is not to route the destination multicast address in multicast BGP or in the static RPF verification. What I need to do is tell my R9 that it is okay to receive traffic from this destination someplace else. So let's use the static one here. So I'm going to say IPM route, and I'm going to say this. So this is the source network that I need to route, and I'm going to say, you know what, it's okay to receive this traffic from this serial interface here. So if I do show IPM route, if I do show IP RPF 192.168.45.0, I will see now that I do have a static RPF that points to a correct interface. But I still have a problem because ping is still failing. Now take a look at the problem on R9. If I do show IP PIM BSR, I don't have information for the BSR. Why? Because this information is actually coming from this IP address here. I will also need to correct the RPF for RP. Now, what I can do here is, instead of using this one IPM route, I can say IPM route and tell the router, you know what, it's okay to receive any multicast traffic coming from this interface. So now if I do show IP RPF this, I will see now that what is actually used for RPF verification is the static mRoute that allows for all traffic to arrive. So at this point here, well, actually not yet, because we need to hear from the BSR, show IP PIM BSR. That's going to take some time, so we can maybe debug it. So debug IP PIM BSR. Let's wait for the packet to actually be sent by R4. So it wasn't sent yet. So we can see show IP PIM BSR. Let's see when the packet will be sent. So we can see that the next bootstrap message will be in 15 seconds. 9, 8, 7, 6. Now, should be going out soon. 2 seconds, 1 second. The message has gone out, reached R2, reached R6, and by now should have arrived to R9. And we can see that we actually do have the BSR information. At this point, our ping here actually works. So at this point here, we have corrected the multicast RPF problem. Now, you can use also multicast BGP for this purpose. But one thing before, I'm not going to use that example now, but order of RPF verification is as follows. So the first thing that is going to be checked is unicast routing table. Then we are going to have multicast BGP. And 3, we are going to have static. But the problem is that the order is actually this way. So it is, again, upside down. So unicast routing is last, static is first, multicast BGP is like this. So here, 1, 2, 3. So this is the order of preference. Now, that means that static will win over multicast, BGP will win over unicast routing. But it's important is that it's a first match rule and not most specific match. And this is the reason why our multicast route here that I used. So here, if I go to R9, if I do show run include IP mRoute, I see that I have a static default mRoute pointing to serial 020. But if I do show IP route 192.168.45.0, I see that this is still pointing to this interface. If it was the most specific match, this would win over this one, but it doesn't because it's the first match rule. So this is pretty much it that you need to know about the static RPF verification and about correcting the RPF failures in your lab.